The students, our topic today is Cauchy's residue theorem. Again, this great man, this great mathematician, he has so many things to his credit. Here is one more thing: Cauchy's residue theorem. This theorem enables us to evaluate integrals. Integrals not only complex but also real integrals. And how does it do it? Let us see how does it do it. To begin with this, let us consider a complex plane where we have a function fz that is everywhere this differentiable, everywhere analytic, except possibly at a few points called singularities. Suppose this is a closed loop in that complex plane. It has we label it as C. It is traversed in anti-clockwise direction as usual, that is our convention, and then it encloses certain singularities within it. For simplicity, let us begin with two singularities first. Let z1 be one singularity and z2 be another singularity within this. These are two singularities of this function fz. I'm sorry, I have not mentioned function yet. I am talking about singularities. These singularities are of fz. We want to evaluate loop integral of this fz along this loop, along loop C. We want to evaluate this integral. In order to evaluate this integral along this loop Z, we face some difficulties. Difficulties that this loop encloses two singularities, and we have done some problems on this when we solved those when we actually completed generalized Cauchy's integral formula, and we saw in that, first of all, Cauchy's integral this theorem, Cauchy's integral theorem, not formula, that enables us to deform this loop C in such a way that instead of this loop C, we cover these two singularities with appropriate these circular this, for example, these contours. Say, let me call this C1, let me call this C2, and then our Cauchy's integral formula told us that this loop integral around C is equal to sum of the loop integrals around this, that is integral C1, loop integral along C1 fz dz, plus loop integral along C2 again fz dz. This much we have learned and we have solved problems based on these, that is there. But now we now suppose we have now this fz, and then fz can be expanded in Lorentz series expansion. We will write it is Lorentz series expansion, which is sigma n equal to minus infinity, and goes from minus infinity to this from minus infinity to plus infinity cn z minus a, z minus z1, sorry, z minus z1 if we are using it here for C1, then z minus z1 raised to n, and if we are using it for this, then it will be z minus z2 raised to n. We are expanding about z1 here in case of C1 and about z2 in case of this. This this what we call this Lorentz series expansion. Let's substitute these there, and then we will get integral C fz dz is equal to this integral C1 fz, in place of fz we have n equal to minus infinity to plus infinity cn z minus z1 raised to n, that is one. And then we have then integral C2 again sigma n equal to minus infinity to plus infinity cn, but let me call this cn1, because cn1, that means it belongs to this. It is not necessary that these coefficients will be equal, because the this is valid here in this disk, and that is valid there in this disk. So it is not must that coefficients will be same. So I write here Cn2 z minus z2 raised to n dz. Of course there is dz for this and dz for this. Now we go to next page and write it there. We have this expression for fz dz. Fz is integral fz dz along c is equal to integral c1 n equal to minus infinity to plus infinity cn z minus a raised n plus dz, then plus integral c2 and this is 1 here, and this is n equal to minus infinity to plus infinity c minus 1 not minus 2, sorry, it is 2 c2 here, c2 and cn2 rather, z minus a raised to n dz. These are our two integrals, and then we have now this is its own convergence disk, and this is its own convergence disk. The disks are different. Okay, in general they are different. So that much. Now proceeding ahead, what I am going to do is that I know that this and this. Let me remind you, we in our this complex analysis, we had an integral. We named that integral important little integral. Sorry, it is z1. Sorry, it is z2. We have become habitual of using a. Now z minus z minus z1, or for time being, to remind you, because you might have used a there, as I have been using, raised to n dz integral around some closed loop, and then what we found, its value of this was z minus a raised to n dz c. It is not necessarily this c. I mean, I can use this, say c1, for example, c1, and then I have this integral, value of this integral 0, except if provided n is not equal to minus 1, 2 pi I if n is equal to minus 1. This was the integral that we did when we were studying Cauchy's integral theorem. We did it, and at that time I told you that we're going to use it more and more. So I am using this. I named it at that time. I called it important little integral of complex analysis. Very useful integral. And now, if I substitute it there in this or this, a miracle happens. What is the miracle? Miracle is that all the terms here, all the terms vanish except one term, that is where n is minus 1. Only that term remains, survives, where n is minus 1. Same is the case here. So no need to use these summation symbols. So we reach then this stage where we have fz dz c equal to c1 here, and this coefficient, the only coefficient left with us is c minus 1, and we have here 2 pi. In place of this we have 2 pi. Its value is simply 2 pi. The whole integral goes 2 pi. That is the magic played by this. The whole integral z minus z1 raised to n, that goes, leaving behind 2 pi I, and only one coefficient, that is c raised to minus 1, because this survives only for minus 1. And same is the case there. We have again, I will write it here, it is C1 minus 1 here. In place of n, I have to write minus 1. N is equal to minus 1. The same is here. C2, and in place of n, I have to write minus 1. Only one term will survive here. All terms will go, and you will have again 2 pi I. Now, my dear students, you can take this 2 pi I out, and when you take them common, 2 pi I, what is left behind is C1 minus 1 plus C2 minus 1. Minus 1 tells us that, it reminds us that only this coefficient remains, which is n equal to minus 1. Please remember this. This is called residue. We call this residue. That is something that was left behind by this little integral. Only this thing was left behind. We have other than 2 pi. Other than 2 pi, we say this is left behind. This is called residue. Residue at z equal to z1, and residue at z equal to z2. This is residue at z equal to z1, z equal to z2. Now, and this is called residue theorem. Cauchy's residue theorem. So wonderful, very interesting. Now, what is this? That means we can evaluate this integral merely by evaluating its residues at two places. One is residue at z equal to minus 1. The other is residue at this residue, yes, of course, z equal to z1. Another at z equal to z2. So calculating residues, and then you get this integral. That is the residue theorem. Now, before we see, we have now, it means that we have to be careful about these residues. Everything is here hinged on these residues. Residues are very important for us. Let's now take this C minus 1 for we have, you know that our this expression for Cn is if you remember, it was Cn, expression for Cn in this Lorentz series was, even I do not properly remember it, so let me say it was, yes, of course, it was 2 pi I integral C 2 pi I integral C f gamma d gamma divided by gamma minus a raised to n plus 1. Same was the case for both of them, C1 and 2, both of them. But well, since paths are different, hence the value of Cn's will be different in the two cases. Now, suppose therefore C minus 1 along path 1 will be equal to 1 by 2 pi I integral C1. Now, path used is C1, f gamma d gamma divided by gamma minus a raised to n is you know, it is minus 1 plus 1 that goes, and this is the residue, 1 by 2 pi I integral C1 f gamma d gamma. Okay. Similarly, we have C minus 2, the two residues. The most important thing for using, before we use this theorem, we will first go for, before using this theorem, we will go for this evaluating residues. How to calculate residues? We must develop some method, a method that we will then stick to in order to be able to calculate these integrals using a residue theorem. So let me go to that part of it. How to calculate residues. How to calculate residues. So we have here this. Suppose we start with this thing. We have, say, suppose this fz, our fz, which has a pole, say a simple pole at z equal to a. At z equal to a, it has a pole. Now I can write this fz in Lorentz expansion. I can write fz as, since it has a pole at z equals 0, this means that it will be having z minus 1 as one of the factor in the denominator. So it will be having this 1 by in this Lorentz expansion, it will be having this c minus 1 coefficient and then 1 by z minus a. That's why it has the pole at the a. Plus, then if it has a c minus 1 coefficient corresponding to this term, why we write c minus 1? Because it is the first negative power of minus 1, that its coefficient is called c minus 1. Then after this negative power minus 1, what else we then have after minus 1? What minus 1 is hereby it is followed by 0, then 1, then 2, then 3. On this side minus 2, minus 3, but we cannot have this minus 2, minus 3. Why? Because if we have minus 2, then it means that we have another pole, that is 1 by z minus a squared. It will be this. Let me show you in order to avoid any confusion. Suppose I have c minus 2. It is coefficient. Okay, c minus 2, and then 1 by z minus a squared plus c minus 1 by z minus a raised to 1 plus other terms. That means I have started from this c minus 2. But in that case, you have a pole which is not simple. You have a pole of second order. Whereas I want to start with the simplest case, in which I have a pole, simple pole. That means of first order. For that matter, I will have to start. It means that my fz does not have these terms, none of them. My fz will be having terms starting from this. That means I have this. This is my this fz. My fz is c minus 1 by z minus a plus then not c minus, after minus 1 you have 0, c0 into 1 by c0, and then this is minus 1 power, then z minus a will have 0 power. 0 power, that means it simply is 1, plus then c1, 0 will be followed by 1, z minus a will have 1 power, then c2, z minus a will have 2 power, and dash. These terms will not create any poles because they do not have anything adverse in the denominator. This is the only term, and hence as I assumed, my fz has just one pole, not many poles, just one pole. And with this thing, suppose I do one thing. Which is the term that has n equal to minus 1? This is this term, n equal to minus 1. Okay, and n is equal to minus 1. Now, what is the residue of this at z equal to a? At z equal to a, residue of this function is coefficient of that term, in which n is equal to minus 1. Now, term in which n is equal to minus 1 is this. Coefficient of that term is this. Then this means this is the residue. C minus 1 is the residue. The question is how to recover it from this. Once again, let me tell you once again, residue term is that term for which n is equal to minus 1, because that is the only term that survived in our this contour integral. Integral fz dz. That's the only term. This means that this is the residue. This residue is not the term which survives. Residue is the residue. If you go back, residue is just this coefficient. Residue is the coefficient, not the term. Not the term, coefficient. That means this is the residue, c minus 1. Now, how to recover this c minus 1 from this? Here is a tricky way of recovering this c0. Tricky way. What is that? Multiply this whole expression. Multiply it with you have here C, this was C1, this is C2. Okay, multiply it with Z minus A, this pole Z minus A fz. You will remove, you will create a new function and thereby remove this pole. Z minus A into fz is equal to C minus 1. Now when you multiply this by Z minus A, you get this. Multiply this by Z minus A, you get this. Then multiply this by Z minus A, that is C naught Z minus A. Then multiply this by Z minus A, C1 Z minus A squared plus so on. Now do one more thing. Our goal is, our destination rather is C minus 1. How to obtain this now? Let's take, let Z tends to A. Let's take this limit Z tends to A. Z tends to A. Now, as Z tends to A, this term will tend to 0. Z tends to A. This term will tend to 0. But do not be under the impression that this should also tend to 0, because it is Z minus A that will tend to 0 definitely, but then there is something more multiplied. This is multiplied with fz. Who knows, in fz there may be a factor that is Z minus A in the denominator that may cancel this, so it will not tend to 0. So the only one factor tends to 0. We don't know the behavior of the other factor as well, and right now, so you cannot take it as 0. You can take it as 0 because this constant, these are constants. So Z tends to A, then this will have this impact. This will go, this will go, this will go, these will go. You will be left with C minus 1. C minus 1 is equal to limit Z tends to A, then Z minus A fz. So simple. So for a function with only one pole, here is the formula for residue. How to calculate the residue? Let me go to this side and I write here, record here rather. Function with fz with single pole. If it has single pole, then formula for residue C minus 1 is, formula for that is this: limit Z tends to A, limit Z tend to A, Z minus A into fz. Just let's keep this written here for ready reference at a later stage. Now let's go to another this case. Suppose now we have pole of nth order. So we have pole of nth order. We will now extend our this analysis from this pole of first order. We will now go to pole of nth order. If there is a pole of nth order, as I told you, Lorentz series will be of this form. It will start with C minus n, nth order pole, and then 1 by Z minus A raised to n plus C. Then this will decrease this n. This will be n plus 1. So it will move towards positive numbers. For example, this is say minus 6, then this will be minus 5, then we will go to it is like this: 0, then minus 1, minus 2, minus 3, etc. As you come from this, you are coming towards positive these positive terms. You are coming towards positive terms, and in the process you are adding 1 to these numbers in order to make them closer and closer to these. Sorry, it is not that. Sorry for this. Yes, now we have this is our this next we will be having here 1 by Z minus A raised to n minus 1. This is it is n order, n minus 1. Then similarly we will have dash dash dash, and then likewise this order will go on decrease till we reach 0, c0. And where will be c minus 1? C minus 1 will be somewhere here. It will be here. Plus, I will write that dot 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 plus c minus 1. So it is c minus 1 here, divide into 1 by z minus a. Then next I will have c 0, c0. Then I will have c1 z minus a. Then I will have c2 z minus a square plus dot dot dot, something like that. Okay, now I want to recover this c minus 1 from this. If I want to recover c minus 1, maybe you would suggest to multiply again by z minus 1. When we multiply this by z minus 1, it's okay. Here we are left with z minus 1 raised to n minus 1. When we will multiply it by z minus 1, there will remain in the denominator, this factor will remain still. Even if you multiply by z minus 1, the factor of z minus 1 will remain here in the denominator. It will not cancel as it did in the previous case. Look here, and when you multiplied by z minus a, there was no factor left in the remainder. The only factor that we had in the remainder was z minus 1, z minus a, that was eliminated. I'm sorry, dear students, sometimes I am using z this a, or sometimes I am using z1 z2 for it. You will excuse me for this, you will bear with me for this. This mistake may occur. I will try my best to not to commit this mistake, but even if it still happens, you will pardon me. You will yourself adjust what this man is speaking about. Okay, now, so we have this here, fz is equal to this. So this will not help us if we multiply by. No, then you would suggest, sir, we should multiply by z minus a raised to n. Yes, that is good, because z minus 1 z minus a raised to n, if you multiply it, z minus a raised to n, okay, into fz. Okay, that will give us c minus n. It will be eliminated, and there will be no z minus a in the denominator, because when multiplied by z minus a raised to n, multiply this by z minus a. For example, suppose here is z minus a raised to n. Now this n minus 1, this n, this means that you will be left with a factor in the numerator, that will be c minus 1 into z minus a. Then you will have it was c minus 1, this was c, and plus 1. Okay, then plus dot 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 plus c minus 1, and when you multiply this by z minus a, you will have a factor z minus a raised to n minus 1 plus co into z minus a raised to n. Okay, then similarly here. Now the problem is that it doesn't serve our purpose. Why? Because we are still, I wanted to recover c minus 1, but what I recovered is c minus n. That is the problem. I wanted c minus 1, but I got c minus n. This is not my requirement. My residue is c minus 1. So what should I do? Here I go c. Suppose I have again I say, suppose this creating problem. Now z minus a, again we go back to this, z minus a raised to n fz is equal to, we can write this as c minus n. Okay, c minus n. Then we have c minus n into minus n plus 1. Sorry, next. Then we have 1 by z minus a raised to n minus 1 plus dot dot dot. And when we multiply it by this, we get this thing, c minus 1 c minus n, okay, plus c minus n plus 1. Then sorry, this is sorry I should, it is c minus n, then Right from this you have z minus a plus c minus n plus 2 z minus a squared plus, if I go like that, proceed ahead, I reach c minus 1. At that time, what should be this z minus a raised to what? Now we can go back and see there what it is. C minus 1 raised to, say, suppose for example, sorry, we have it is c minus 1, z minus a raised to n minus 1, z minus a raised to n minus 1 plus dot dot dot. Okay. Now, what we observe? We observe an interesting thing. What is that? We observe, we have on this side, we have, although we failed in getting c minus 1 till now, there's an indirect method of getting this c minus 1 from this expression. If we just realize one thing, and what that thing is, if we realize that we have here this this is this right hand side of this equation is simply Taylor series expansion of this function. I mean this whole function. Taylor series expansion of this. Of course, I have to write these. There are these. This first term should be value of the function at, say, z equal to a. Second term then should include, it has z minus a, and it should now include first this derivative. Then it means this is the first derivative. First derivative f dash a. You must be remembering this. Then we have this second derivative. Then similarly third derivative. Now, which derivative is this? The question is, which derivative is this? Let us see which derivative is this. Because this is the secret of all this. I want c minus 1. I have found one information. I have got one information about c minus 1. It is the derivative or in Taylor series expansion. The only problem is now it is the derivative in Taylor series. The only problem is now we have to identify which is that term, the number of the term, whose derivative it is in Taylor series expansion. Now, see, suppose this term is the jth term. So let us see how. First term n plus 1 minus n plus 1. Second term minus n plus 1, n plus 2. Second term this. First term this. First derivative, I mean. I'm not counting this because it's not derivative. First derivative this, second derivative this. And if I continue, this must be that. Suppose this is jth derivative. Suppose this is jth derivative. Jth derivative means here I have then this. In this case, I have j equal to n minus 1. How do I know j equal to n minus 1? Looking at this, n minus 1. So see, second derivative 2, first derivative 1. Similarly, if you write third derivative, you will get. Similarly, this must be value of, you have n minus 1. I write j for this. Then j is equal to n minus 1. It means that c minus 1 then is, c minus 1 simply is then, that is equal to the which derivative it is. C minus 1 is then n minus 1th derivative. Simple, and no need to this bring j at all. It is the n minus 1th derivative. First derivative, second derivative, third derivative. This power tells me it is the n minus 1th derivative. Now, if it is n minus 1th derivative, you know value of the derivative. In Taylor series expansion fn x, let us take this fn x divided by n factorial. This is the derivative there, and then we have rest x minus a raised to whatever it is, raised to n. Okay, now you have this derivative, nth derivative. Here you have n minus 1th derivative. So this will be this c minus 1 will be n minus 1th derivative, n minus 1th derivative. Hope that you have understood this. I can once again revise it a bit. I have written this Taylor's series expansion, and in this Taylor's series expansion my target is c minus 1. I want to get this. Previously I thought I could get this by multiplying this fz by z minus a raised to n, but then I had to cut a sorry figure because it yielded c minus n but not c minus 1. However, I quickly recognize that this is Taylor's series expansion of this function, and of this function, not fz, of this function, please. Taylor's series expansion of this function, and my coefficient c minus 1 is the derivative. Taylor's series involves derivatives. Now it is the derivative of which term? N minus 1th term. So it is the derivative. That is why I write c minus 1 is equal to n minus 1th derivative. And what is the expression for n minus 1th derivative? You have nth derivative, that is this, and n minus 1th. Now see, 1 divided by, first of all, 1 divided by n minus 1, its number. This is n factorial. Here it will be n minus 1 factorial, n minus 1 into, now this is this much, then the derivative of what? Yes, derivative of this, derivative of, say, nth derivative of n minus 1th derivative, not nth, n minus 1th derivative, because the number here is n minus 1. N minus 1th derivative of what? Derivative of this function z minus a raised to n into fz into fz. Okay, and then what we do, we take limit of this, or rather we take simply value of this at z equal to value of the derivative. You have not to write this. It is actually incorrect that I have written it. It is f and a, value of the derivative at a. So you have to take z equal to a. In that means in this you will have to substitute z equal to a. Or you can write here limit z tends to a, value of this. So this is, my dear, our general formula for this residue. General formula for the residue. So ultimately we have found this formula. Residue is equal to, we will simply write it as residue is equal to, let us see this. Residue is equal to 1 by n minus 1 factorial, n minus 1 factorial d by dz, dn minus 1 by dz n minus 1 z minus a raised to n fz. Now let me see, yes, fz, and this is to be evaluated as z equal to a. Okay. Now, so what is n here? N is the order of the pole. What is the order of the pole? That is n here. And then a is the point around which you are expanding, or the point of singularity. This is the point of singularity. So this formula will be our. There are many formulas, but all of them spring from this. All of them. So we should watch out this general formula for this, and then you need not at all go for, say, for example, individual formulas that will simply create a mess. So in order to avoid that mess, I encourage you to keep this with you, and if you keep this with you, you will enjoy rest of this, whatever we are left with in complex analysis, that you will find highly enjoyable. But keep this thing with you. It is this formula which reduces, for example, to this that what we found in the first case, pole of, for example, in first case we took pole of first order. You can, this is that formula. This, I mean, this c minus 1 is equal to this. This formula follows from that pole of, you can check it. can check it. If pole is of the first order, n is equal to 1, then residue will be equal to, I will not write or, because or we usually write for radius of convergence. Residue will be equal to 1 by 1 minus 1, that is 0 factorial, d 0 by dz 0, because 1 minus 1, that is z minus a, n is equal to 1, n is equal to 1, fz. Now it means, and to be evaluated at a, z equal to a. Now 1 by this residue is equal to 1 by 0 factorial, that's 1. This is you are not going to differentiate, so you are left with this z minus a fz, but value of this at z equal to, or the same thing that you could say limit z tends to a, this. So you better remember this lost this formula. Better remember that. Then this formula. It is better to remember this lost formula than to remember those individual formulas. In next video, we will be using this formula. We will be using extensively in going for after these problems based on this Cauchy's residue theorem. That will be our last video, if God wills, about this complex analysis. Thank you so much.